A stationary wave forms when two progressive waves with the same frequency superpose as they're travelling in opposite directions. Points in antiphase form nodes, areas of no displacement, and points in phase form antinodes, maximum displacement. The separation between a node, or antinode and antinode, is equal to half the wavelength of the original wave. The frequency stays the same. As the waves travel in opposite directions, there is no net energy transfer. In between nodes, next or adjacent to each other, all the particles are in phase, which means they're all reaching maximum displacement at the same time. On different sides of the nose, the particles are in antiphase, with particles on one side reaching maximum positive displacement at the same time as particles on the other side are reaching maximum negative displacement. A stationary wave can be formed by reflecting microwaves off a metal sheet. The two waves travelling in opposite directions creates nodes and antinodes, and a microwave receiver can detect the changes in intensity between the node and the antinode. A string which is stretched and fixed at the two endpoints, which act as nodes, can form a stationary wave. If it is plucked, a progressive wave travels along the string and is reflected from the end. As the reflected wave is travelling in the opposite direction to the original wave, they are superposed and form a stationary wave. Now it's time to get technical. This diagram gives a few examples including the frequency in relation to f0 and wavelength of different harmonics and what they look like too. The speed of a progressive wave is constant if the tension is fixed, so by using the wave equation speed equals frequency times wavelength, we see that if the frequency is doubled, noted as 2f0, the wavelength is half that at f0, which is the fundamental frequency. To see this yourself, you can use a vibration generator to create nodes and antinodes on a string. This diagram is known as Melday's experiment, and with it many controls can be changed, such as a tension, speed of vibrations, and the length of the string. Stationary waves can be created in air columns, whether they're open or closed at one end. In a closed tube, there is a node at the closed end as the air can't move. At the open end, there is an antinode, the point of greatest oscillations of air. In an air column, the fundamental mode of vibration simply has a node at the closed end and an antinode at the open end. From a node to an antinode is a quarter of the wavelength. Harmonics can also occur at odd multiples of the fundamental frequency, like 3f0 or 5f0. In open tubes, there must be an antinode at each end to form a stationary wave. Any multiple of the fundamental frequency is possible, and a few examples are shown on the diagram. To work out the speed of sound in a resonance tube, you must first know one thing. The wave doesn't end at the top of the tube as it looks like on the diagram. The measurement from the top of the tube to the antinode at the top of the wave is known as C, or the end correction. To work it out, you draw the diagram. For the first harmonic, the length of the tube above the water is L1, and L, the length, is equal to a quarter of the wavelength. For the next harmonic, the length of the tube is L2, and L is equal to 3/4 of the wavelength. The wavelength over 4 is equal to L1 plus the end correction, and 3 times the wavelength over 4 is equal to L2 plus the end correction. If they're minus from each other, we see that half a wavelength equals L2 minus L1, and a whole wavelength, rearranging the equation, is equal to 2 times L2 minus L1. We will know the frequency of the fork that's been used, so now can find the speed of sound using the equation v equals f lambda, or speed equals frequency times wavelength. You can see this on the diagram.